Random variable is a variable that can take on different values depending on the outcome of a random process, such as an experiment. Random variables can be discrete or continuous. Discrete variables are whole numbers. Think of them like that. So they're whole values. They can be counted, in other words, 1, 2, 3, 4, 5. Continuous variables can be measured and can be written as fractions and decimals. So discrete, you would say, you know, how many cars are outside, how many cars. That would be a discrete variable. So you would say 2, 3, or 4. You can't say 2.5. Continuous variable would be, you know, how tall are you? You could say 1.83 meters. That would be a continuous variable. Okay. I guess the first thing you learn is to understand, you know, is it a discrete or continuous? I think we understand that. Is anybody wanting me to actually go through some of these basic examples? The number goals? No, yeah, I didn't think so. These are easy. You got to learn how to write the set of possible values for each discrete random variable. So very easy. The number rolled on a die would be any number from 1 to 6. So you could write X, any number from 1 to 6, all the elements from 1 to 6, inclusive of 1 to 6. Find the number of girls in a family of 3 children. So you could have no girls, 1 girl, 2 girls, or 3 girls. You could write it like this. Or you could write the set as X is 0, 1, 2, or 3. The number of heads when tossing a coin 8 times. You could have 0 heads, 1 head, 2 heads. I think you guys get it. Any questions? No, I didn't think so. It's pretty easy. We'll move forward. Discrete probability distributions. So it's a distribution, which means it's a range. List the probability for each value of a discrete random variable. A discrete probability distribution can be displayed in a table or graph or represented by an equation or set of ordered pairs. It is also called a discrete probability function. We can write a probability function that uses X as the random variable as this. So P of X equal to little x or P of X. But don't mix up P of X to your polynomials. This is probability. So most of the time you probably see us using this version. Okay, and it's very straightforward. It just looks like this. So in a random experiment, a die was rolled and the results recorded in the table below. You know, you rolled once, 18 times, you rolled 2, 23 times, blah, 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 blah. How many times was the dice rolled or the die rolled? You'll just have to add them all up. Draw up a probability distribution for this experiment. Okay, so the way the probability distribution works, which we're going to draw up in a second. Actually, I'll rather just do it together. But the way it works is it's just your probability of each event occurring. Cool? So you'll see that in a second. And then write the probability function. All right, we'll just come back to it. Let's answer each question. So solution. Adding the frequencies, the die was rolled 120 times. So how many times was the dice rolled? Add them all up, 120. Draw up a probability distribution for this experiment. Ready? There it is. So X is 1, occurred 18 out of 120 times. That becomes a probability of 3 over 20. X equals 2 times. Rolling a 2 was 23 out of 120. Rolling a 3, 17 out of 120, blah, 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 blah. So your probability distribution is just a fancy way of saying, find me another column that just allows me to write my probability of each event occurring. Cool? So a very fancy way of saying that. All right. All right, so draw up your probability distribution for this experiment. There it is. B, write the probability function of rolling a die as a set of ordered pairs. So this with this. So again, that's just a fancy way of saying if you can get a 1, it occurs 1 out of 6 times. If you can get a 2, it also occurs 1/6 of the time. If you get a 3, it occurs 1/6 of the time. If you get a 4, the probability of getting x equals to 4 is 1 out of 6 times. If you get a 5, the probability of that is 1 out of 6. The probability of 6 is 1 out of 6. Cool? A probability function for discrete random variable x is given by this. So that's just, it just says it is this particular function, like it is, you know, I mean, okay. The function could be, you know, we were saying x squared for x is less than 0. It could be 5 for x is greater than 0. And that's it. Let's just say if it was those two, greater than or equal to 0. That's what we were doing before when we were doing functions, right? This time it's just applied in terms of probability. So the probability is this if it is between 0 or if it is 0 or 2. The probability is this, the distribution is this, if it's 3 or 4. And the probability is 0 if it's any other x value. So if it's 1 or 5 or 6, it's 0. Complete a discrete probability distribution table. That would look like this. So when it's 0, so like I was saying, when it's 0, you sub it in. You will get, when it's 0, you get a sub it in, you get a quarter. When it's 2, you sub it into that one as well, you get an eighth. When it's 3, you sub it into the next one. When it's 3, you sub it into this one. And when it's 4, when it's 3, it's a quarter. When it's 4, it's 3/8. When it's anything else, so when it's 1, it's 0. When it's 5, it's also 0. When it's 6, it's 0, for example. Cool. And that's how that looks like. So 0 when it's a quarter. Probability of that occurring is a quarter. 1, it's 0. 2, you'll get an eighth. 3, it's a quarter. 4, you get 3/8. What must the probability of everything add up to? If you've done it right, it has to add up to 1. And what else do we have? Evaluate that the probability is odd. Okay, we can get up to this. I think once we start doing questions, we can get to this. This is a bit annoying going back and forth. So remember that all probabilities will lie between 0 and 1. Their total is 1. These same rules apply to a probability distribution. So for a discrete probability distribution, all possible values must be mutually exclusive. That means they can't rely on each other. That's okay. The sum of all probabilities must be 1. For each value of x, it must be, the probability must be between 0 and 1 and inclusive of 1, which just means what we know. Your probabilities can't be negative and they can't be greater than 1. Okay, so here we go. Let's have a look at this question. Consider this discrete probability distribution. X is 1. The probability of that occurring is 0.2. For x equal to little x, right? 0.2, 0.35, 0.1, 0.15, 0.05, 0.15. So let's say if this was a die, right? 1, 2, 3, 4, 5, 6. The probability of getting a 1 is still 1 over 6. Sorry, the probability of getting a 1 is 1/6. So that doesn't change. It's just that as you rolled this die maybe 100 times, we realized that 1 occurred 20% of the time, 2 occurred 35% of the time, 3 occurred 10% of the time, 4 occurred 15% of the time, 5 occurred 5% of the time, 6 occurred 15% of the time. Does that make sense? All right. The questions will say, find the probability that capital X equals 2. Okay, well, capital X equals 2, remember this is little x now. That means just X is 2, which is here. So for the probability of it becoming 2, it's just 35%, so 0.35. So the probability of X equal to 2 would be 35%. Are we able to read that fully? We completely understand that. Is anybody that's confused? Okay. Double I. Find the probability that x must be smaller than 3. So x must be smaller than little x being 3. That means 2 and 1. So the probability of obtaining 2 and 1. So the probability of 0.35 plus 0.2 becomes 0.55. What's the probability of x being greater than or equal to 4? Well, that would be this plus this plus this, right? The probability of x being greater than or equal to 4, that means picking up 4, 5, or 6. And that's it. And then what's the probability of you picking a number that is between 2 and inclusive of 2, but not inclusive of 5? So that means 2, 3, and 4, which would be 0.35 plus 0.1 plus 0.15, which is 0.6. Show that the sum of all probabilities must be 1. I think we understand that. You know, this plus this plus this plus this plus this plus this must add up to 1, must add up to 100%. And then draw a histogram of the function. Histogram's easy. There's your numbers, 1, 2, 3, 4, 5, 6. There's your scores, x. There's your probabilities, p of x. I guess the rule that you guys need to remember is your histograms must be drawn in the middle of your numbers. So like that's a 1. Don't draw 1 there, 2 there. That's wrong. It's going to be 1, 2, 3, and then it's just column graphs, really. Any questions for me before I move on? This looks like an interesting question. Let's have a look at what it's saying. A function is given by p of x equals x minus 1 on 3. So that means we know this bit here was, so I'm sure this is not for this question, but just so you know, this bit here was calculated by x minus 1 on 3. So if you were thinking of it in terms of a dice, it's saying that it's not always a 6th. It's not, I mean, it's still, I guess it's biased. Is it biased? Ooh, it's tricky to say biased. Look, it's not even. It's not going to always be a 6th. It's defined by a function. And the function, as the variables change, like as it becomes 2 or 3, the probability changes as well. Whereas in a normal die, it's just always going to be a constant 6th. So a function is given by this, where x equals 1, 2, and 3. Is the function a probability distribution? Well, the best way to find out is you're going to sub in your 1, 2, and 3 for your x values. There it is. As long as your probabilities add up to 1, it is a probability distribution. The function can be a probability distribution. That means it can be represented in terms of probabilities, not just by a function. So like this guy, if I said p of x is equal to x squared, would that be a probability distribution? Well, if I do p of 1 is 1, p of 2 is 4, p of 3 is 9, add them up, that gives me obviously greater than 1. That is not a probability distribution or a probability function. Does that make sense? So this would not be a probability function. Is this function a probability distribution? Absolutely. Why? I subbed in 1, 2, and 3. I worked out the probabilities of each event occurring. The probability of obtaining a 1 is 0. Probability of obtaining a 2 is 1/3. Probability of obtaining a 3 is 2/3. Add them all up. The probability of the whole event, is equal to 1. Okay, find the value of n for which the table below is a discrete probability distribution. Well, if you know it's already a probability distribution, what must each of these items add up to? each, sorry, not each, what must the whole summation of all 5 of these terms add up to? It must add up to 1. So all I'm going to do is very simple math. You just add up all of this and then subtract it. So add it all up. 112 plus 1 on 6 plus 5 on 12 plus 1 on 12 plus n equals to 1, and then 1 take away 9 over 12 equals a quarter. Now you know that becomes a quarter, for example. Okay, any questions there? Okay, I'm going to move on. Let's have a look at these. Interesting. All right. A game involves scoring points for selecting a card at random from a deck of 52 playing cards. A game involves scoring points for selecting a card at random from a deck of 52 playing cards. The table shows the scores awarded for different selections. Okay, so if you were able to, if you selected a number from 2 to 10, you'll get 2 points. If it was a picture card, which is a jack, queen, or king, you get 5 points. If it's an ace, you get 8 points. All right, you got to work out how many of each cards there are, right? You got to work out that there's 4 of these. There's 12 of these. That is 12, 16. Yep. So there's 36 of these. Are we all comfortable with that? There's 52 cards altogether. 4 of these, 12 of these, 36 2 to 10s. Yes? Okay, so what's the probability that I'm going to get this? What is the probability that I'm going to obtain a number that is between 2 to 10? Well, the probability of a number between 2 to 10 is 36 on 52. Your basic probability stuff that you've been doing, right? What's the probability of it being a picture card? Jack, queen, or king? Well, that'll just be 12 out of 52. What's the probability of getting an ace? That's just 4 over 52. So the question says, draw a probability distribution table for a random variable y for the different scores. What's the probability of getting a score of 2? Well, that's the same as picking a number, 2 to 10, right? So probability of score of 2 is 36 out of 52, 9 out of 13. What's the probability of you getting a 5? Well, that's the same as you obtaining a picture card, 12 out of 52. What's the probability of getting an 8? It's the same as getting an ace, 1 out of 13. You guys comfortable? Yeah.
There's only 4 2s in a deck.
There's only 4 2s in a deck.
Yeah.
Yeah, but
so wouldn't it be
score,
4?
no. So these are scores.
Oh, score of. Oh, okay.
Yeah. Score of 2, score of 5, score of 8. You can you'll get a score of 2 if you pick a 2, 3, 4, 5, 6, 7, 8, 9, or 10. Does that make sense?
Yeah.
Yeah, and I was trying to say, like, you getting a score of 2 is the same as you picking any number from 2 to 10. So if I asked you back in like year 9 and year 10, I would have asked, okay, what's the probability of getting a number between 2 to 10? You would have also said 36 out of 52, because there are 36 cards out of 52. Or in this case, you're going to ask, what's the probability of obtaining a 2, a score of 2? Or Sam only gets 2 points. Well, it's still 36 out of 52. So they're the same question, just worded differently now. Okay, good. So there it is. There's your distribution table. Blah, 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 blah. Find the probability that your score will be less than 8. Well, the probability of you scoring less than 8 would be the probability of you scoring a 2 or a 5. Simple. 12 out of 13, which makes sense because the probability of getting an 8 is 1 out of 13. The probability of getting less than 8 would be 1 minus 1 on 13. Do you guys get that? Opposite. you got to know the contrary events, the complementary events. So 1 minus, getting an 8 would be getting less than 8. What's the probability of getting it greater than 2? Y being greater than 2? Well, greater than 2 would be 5 and 8. I think you guys get that now. Add it together. Ugh. Simple. Any questions? All right, beautiful. In a uniform probability distribution, the probability for each value is the same, and I think we just, well, can someone give me an example of when it will be uniform probability distribution? The probability for each value is the same.
Rolling a die.
Yeah, right? That's exactly what I was saying before. That's the rolling of a die. It'll just be each case is 1/6, 1/6. So that's uniform. It's constant. Flipping a coin. Basic questions. I think I've got to move past these. These are too easy for you guys. Oh, what's this? The probabilities are not... Okay, of course. When tossing 2 coins, the number of heads could be 0, 1, or 2. So, you know, you could get a quarter, a half to get a 1 head. Wait, what are we doing? Use the probability tree, find the probability for each outcome. Yeah, so the probability of getting no heads is a quarter. The probability of getting 1 head is a half. The probability of getting 2 heads is a quarter. The probabilities are not the same. This is not uniform distribution. Okay, so when you're tossing 2 coins, the number of heads could be 0, 1, or 2. The number of heads would not be uniform. But when you're here, you've got 1 coin, the number of heads would be uniform, because to get no head is half, to get 1 head is also a half. So it's the same probability. Okay, draw probability distribution table for the number of black balls that could be drawn out of a bag containing 5 black and 3 white when 2 balls are selected randomly without replacement. So you're not replacing. First, draw a probability tree. So it'll look like this: black, white, black, white. Your black would be 5 black out of 8 balls altogether. That's your first turn. First turn. Right? 5 black, 3 white. If you chose a black, how many blacks are left in your second turn? Because you're not replacing. You've got 4 blacks left out of how many balls or marbles are left? 7. 4 out of 7 and 3 out of 7 here. Why is it 3? Because you still have 3 white marbles or white balls if you chose a black one at the beginning. If you want to double check it, this plus this must always add up to 1. That was the rule. So each tree or each branch must add up to 1. So 4 out of 7, 3 out of 7 adds up to 1. If you chose a white, then you're obviously going to have 2 whites out of 7 balls, and then 5 still for your black. And then what you're left with is BB, 2 blacks, 1 black, 1 black, no black, in other words, or what you're used to back in year 10, which is this version. 5 out of 8 times 4 out of 7 would give you the option for 2 blacks. 5 out of 8 times 3 out of 7 would give you 1 black. 3 out of 8 times 5 out of 7 would give you again 1 black. And then white would be 3 out of 8 times 2 over 7 or 2 out of 7. So 0 blacks would just be the last one, what I just said. 3 over 8 times 2 over 7, just plug it into your calculator, get an answer. 1 black would be this and this. So multiply, and then add your 2 answers together. Multiply, multiply, and then add your two answers together. And then, of course, 2 blacks. And done. And then that's your probability distribution table. 0, 1, or 2. And what does 0 stand for? 0. Sorry, what does X stand for? Amount of blacks. So you getting 0 blacks, you getting 1 black, you're getting 2 blacks. Cool. That's how this works. Draw a probability distribution table for the number of black balls that could be drawn. So you guys are more used to this, black, black, you know, black, white, white, black, and white, white. You guys got to understand, we're looking at scores now. So your scores, you got to work them out as how many blacks. 0 blacks, 1 black, 2 black, instead of W, 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 B, B, W, B, B. Okay, any questions? No? All right. Shall we start with a question? Question 4 looks good. Let's start off with that one. I'll give you guys some time to just write it down, if you like. Maybe start A. Okay. A function is given by p of x equal to x minus 2 on 6. For x equals to 3, 4, and 5. Show that the function is a probability distribution. Everybody get that? What I did there? It's really easy. I know the math is really easy. I think for this, and this is just general statistics talk now, it's usually the words that you got to get around. You got to start understanding the words. So the math is not difficult. It's knowing what to do when it says, you know, probability distribution compared to draw up a probability distribution table. Okay. All good. B. Draw up the table. Okay. Aya, let's do this one together, please.
Okay.
Okay. So we're going to write what up here? What's the letter you would write?
X.
X. And then what's the thing we write here? P of X, or
Yeah.
you could write it like this, little x.
Yeah.
Okay, good. Then what are our numbers that we're going to choose for our score? That's too big. Anyways. So what are our numbers here for x's?
3, 4, and 5.
Probability of x occurring?
1 over 6.
And C. The probability that x must be greater than 3 is equal to P of 4 plus P of 5. 1/3 plus 1/2, 5 out of 6. Double A. The probability that your x is going to become odd, you're going to choose an odd x value, which is 3 and 5. So that just becomes 1/6 plus 1/2. 2/3. And then last one. Triple A. Probability that x is between 3 and 5, non-inclusive. No, I really believe I've taught your algebra well enough for you guys to find most of these questions pretty easy. There you go. Yeah. X is between 3 and 5, not including 5, but inclusive of 3, so it's just 1/6 and 1/3, and you're done. Anybody want me to go through anything there? Okay, let's try maybe a harder one. Find K if each function is a probability distribution. Okay, if it is a probability distribution, that means when I sub it in and I add them all up, it has to equal to 1. We understand that now. So P of x. So P of 1 equals 2k. P of 2, 2 plus 1, 3k. P of 3, 3 plus 1, 4k. P of 4, 4 plus 1, 5k. 2k plus 3k plus 4k plus 5k equals 1. Now what's that? 9, 12, 14, so k equals 2, 1 on 14. Hope we're starting to get the hang of this now. Okay, this one, B, x is 0, the probability of 0 occurring is 0.2. X is 1, the probability of 1 occurring is k. X is 2, the probability of 2 occurring is 0.15, 3. So the way you could also read this, another way, instead of saying occurring, you could say, I don't know, let's say in terms of kids, you could say 0 boys, 1 boy, 2 boy, 3 boys, or 4 boys. All right, that's the idea of it. So it's very specific to one particular event, I guess, or one outcome. Oh, it's very tricky to say it like that. All right, I think you guys are getting it, so I'm not going to confuse that. You understand how I'm going to find k. K equals to 1 minus 0.2 minus 0.15 minus 0.34 minus 0.12. .19. 0.19. Okay. C. How do we read this? Hopefully you guys remember. It's read exactly the same as the table here. The probability of getting 1 boy is k. The probability of getting of 2 boys is 1 on 10. The probability of getting 3 boys is 0. The probability of getting 4 boys is 1 on 4, 1 on 5. Probability of having 5 boys is 3 on 10. Probability of having 6 boys is 2 over 5. That's the logic. So to find K, it's very easy. Here's going to go again. 1 minus 1 on 10 minus 1 on 5 minus 3 on 10 minus 2 on 5. One on 10 plus 1 on 5 plus 3 on 10 plus 2 on 5. 1 minus that is 0. So K is actually equal to 0. Any questions for me? They're all pretty much the same. So what I might do is just do another 1 or 2 of the worded problems, and then we'll move on to the next one. All right, I'll give you guys just a minute to quickly read that. Okay. Does anyone have any ideas? Company makes washing machines. On average, there are 3 faulty machines made for every 1,000 machines. 2 washing machines are selected at random for quality control inspection. Draw a probability distribution table for the number of these machines that could be faulty. Okay, so 2 washing machines are selected. So what are the possibilities firstly? Can someone tell me what are the possibilities that, or what are the scores that could occur? What are the likely scores for faultiness of 2 washing machines? What would I be writing? I want to see if you guys actually understand this. Does anyone really know? Anyone want to take a guess?
Is it 3 on 1,000 plus 3 on 999?
No, it's not exactly working like that. So the way you want to pick out your X, we'll need that eventually, your probability, right? But the way you're picking out your X is, that's like your score of faulty machines. Faulty machines, let's say. Think of it like that. Or number of faulty machines. If you're taking out 2 washing machines, what could have happened? How many could have been faulty? Give me the different cases. Andy, if I'm taking out 2 washing machines, what are the different possibilities of having faulty machines?
So
Possibilities I'm talking about. I'm not talking about probability. Like, what could have happened? If you took out, imagine right now, go to Harvey Norman, and you just select any 2 washing machines. What could have happened? You come home, and then what could have happened? They could have both been perfectly fine.
Okay.
Right?
Yeah.
No problem. So that means 0 faulty machines. So both of them are not faulty. What could have happened?
It was faulty.
1 could have been faulty, or both of them could have been faulty.
Okay.
Does that make sense? That's how you're picking out your scores. So same thing with that whole brother case and girls and heads and tails. So the idea is you can have, you can have girl, 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 boy, boy, girl, and boy, boy. But when you're picking out your scores, you're going to go, okay, what's the probability of having one boy? Sorry, of selecting a boy. Selecting boy, it would be no boys, one boy, or two boys. And the probability of no boys is a quarter. The probability of one boy is a half. The probability of two boys is also a quarter. And that's the idea. That's what we're trying to work out. So we're trying to work out these 0, 1, 2 cases. So we're isolating it. Anyways, we'll do some more problem-solving questions. But do we get that now? Like the score of faulty machines is 0, 1, and 2. Again, let's read it again so we can make sure. The company makes washing machines. Okay, on average, there are 3 faulty machines made for every 1,000. I think we get that. So the probability, every 3, there's 1,000 faulty machines. Faulty machines. 2 washing machines are selected at random for quality control inspection. So that means if you selected 2, what is the likelihood that, what is the possibility that they could have been faulty? Would be none, or 1, or 2. None could have been faulty, 1 could have been faulty, or 2 could have been faulty. That's a possibility. What is the probability that none would have been faulty? What's the probability that none would have been faulty? Andy, do you have an answer for that?
997.
997 on 1,000 for the first one, multiplied by?
997 on 999.
I think so, right? Because it doesn't. Oh, I don't think you can decrease because the idea is. I think it should still be that.
But if you take one, wouldn't it decrease?
Doesn't it say on average though?
Yeah, that's the problem. So then shouldn't you not decrease? Is that what you're saying, Greg? Because saying on average?
Yeah.
Yeah, so you're not really selecting, it's not definitely like 3 out of 1,000. It's on average, it's 3 on 1,000. So like, yeah, it's a bit tricky. Like it's a bit, I know what you're saying, the whole decreasing one, but it's not like that for this question. Let me see if I can put you in another example again. 3 faulty machines made for every 1,000. For every 1,000.
Wouldn't it be increasing? Just a thought.
What do you mean by
Because
that?
it'd be 997 over 1,000 times 998, right? Because you're taking one. Wait, what am I doing?
No,
Wait,
don't
wait,
do that. Don't
Wait,
do
wait,
that.
wait. That's,
No, it's not like that. The thing is, it's not about replacing or anything because, like, you're not replacing it. You're not putting it back. You're not taking it away. You're not doing anything like that. The problem, the idea is, it's like the probability of a faulty machine is always this. The probability of not a faulty machine is always this.
Oh, okay.
You know, like it's just, it's not like you're replacing it with anything. It's just that it became faulty. Like, the motor didn't work or something happened. So it's not. Yeah, I know what you guys are doing, but it's just it doesn't work like that. For this case, you're not replacing. This is what I'm trying to say. If you're not replacing or something like that, fair enough. But it's just the probability of it coming out faulty. Like there was something wrong that happened. That's it. It happens. Like it's an error. You know, you might have measured a room you were building, and the room was meant to be 3.35 meters, and you did it to 3.33 meters. I mean, it's bound to happen, but there's an error, and there's a probability of that occurring. And that's what these are. It's not like, oh, okay, it happened, so therefore it won't happen again, or it reduces the risk of it happening again. It doesn't really reduce it. Does that kind of make sense? If I use that application there?
Yeah.
It's an error. That's it. It's an error. It can occur, and that's the error of it occurring. All right. All right. So faulty 997 on. Yeah, perfect. I think we get that now. Probability of 1 being faulty would obviously be 3 over 1,000 times 997 over 1,000. Do we need to go ahead and do the other version, which would be 997 over 1,000 times 3 over 1,000? You don't, because remember, you're not replacing or anything. You're just going, okay, as long as one was faulty, the other one's not faulty. So we're not doing the whole, what if the first one was not faulty and then the second one was faulty, or vice versa. You're not doing that because you're not replacing anything. So it's obsolete. The probability of both machines being faulty is that. And I think we've already answered the second bit. And your probability distribution table, I think we get it. It would have just been, you know, your little nice box. There's your 0, 1, and 2, and then these values are just these numbers here. Does anyone want me to actually do the table, or do we get it like this that I've done? And then find the probability that 1 will be faulty. There it is. At least 1 will be faulty. So it's just this plus this. Okay, let's do another one. Let's get this wrapped around our heads. Maybe we'll go back to an easier one. Maybe this one. Again, have a read first, and we'll try it again together. Okay. Yeah, someone wants to try it, or? Oh, all right, in a game, let's see. In a game, each player rolls 2 dice. The game pays $1 if one of the numbers is a 6. $3 for double 6, so. Okay, so we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. $1 if one of the numbers is a 6, so that means all of these numbers and all of these numbers. Are we okay with that? So if a 6, I'm just going to write if a 6 for now, so you guys can understand how many of them are there. There's going to be 6 plus 5, so there's 11. There's 11 ways of getting $1. Are we okay with that? The game pays $1 if one of the numbers is a 6. Sorry, no. I added 6 and 6. 10. 10 ways, right? Just 1 and 6, 2 and 6, 3 and 6, 4 and 6, 5 and 6. Not this bit. This bit here is a double 6. So if double 6. How many times can you get double 6? I think you guys already know that. That's 1 time. And you'll get $3 and $2 for any other double. If other double. 1, 2, 3, 4, 5. So that becomes 5 times. You'll get $2. There are no payouts for any other results. Other. How many combinations are there all together here, you guys? 6 times 6, there's 36 combinations. So that means that's 10. 11, 16, so 36, so 20 other combinations, right? And you get no payout, so $0. Okay. Any questions at this stage? No? Okay. A. Let's see if you guys can understand what this is, what bit you need to use out of all this. Draw a probability distribution table for the game payout Y. For the game payout Y. So what would Y equal to? Anyone want to take an educated guess what my scores are going to be?
$0, $1, $2, $3.
Yeah, that's exactly it. I mean, the key word there was payout, other than the Y. You're looking for the distribution table for the payouts. So the different things you could get, the different, I don't know, possibilities you could get. I like to think of it as possibility. I don't know, it just works better for me like that. So the different possibilities I could get are $0, $1, $2, $3. And the probability of that occurring is something else. That's the next column or row, sorry. So your Y here, or they use capital Y, but I think it's better to use little y. Capital Y equal little y. There we go, just to show it like that. All right, 0, 1, 2, 3. Again, draw probability distribution table. For that just means draw this value table with P of Y down here for the game payout Y. So for the payout, like what's the probability of you getting paid out? 0. Well, 20 out of 36. What's the probability of you getting paid out? $1. 10 out of 36. What's the probability of you getting paid out? $2. 5 out of 36. And what's the probability of you getting paid? $3. 1 out of 36. And then obviously we've already answered the next bit. Find the probability of winning $3. 1 out of 36. At least 2. It'll be 6 out of 36. And then less than 3. It'll be these 3. 1, 2, 3. 1, 2, 3. If you've done it right, all of these numbers must add up to one whole. We know that it is right because we already know these all add up to 36. So 36 out of 36 is going to give you 1. Andy, does that make a lot more sense now?
Yeah.
All right, we'll keep going. Don't worry. We'll do another one again. More of these ones. Simon plays. I feel like that's okay. Let's see maybe some of these ones. Oh yeah, with replacement, without replacement, doesn't look like that. Okay. You're ready? Start reading this one again. Maybe write a few things that you would do before I start. Okay. A bag contains 7 red, 6 white, 8 blue balls. Create a probability function table for the number of white balls selected when drawing 2 balls. Okay, Andy, sorry that I've got to pick on you, man. I just want to make sure. If you get it, then that means everybody else is also getting it. So let's try it one more time. We're looking for white balls, right? 2 balls at a time. What are you going to say?
Yeah. 0, 1, and 2.
Yeah, no white, 1 white, and 2 whites. Great, thank you. Done. So, and that's all we're going to do. We're going to assume, X is 0, 1, and 2. 0, 1, 2, p of little x. Let's try that way now. What's the probability of getting, okay, sorry, let's do A, with replacement. Okay, if it's replaced and you're getting no white, so that means your very first one had to be a red or a blue, so 15, 7, 8, not yet, 15, out of 21. Oh, this is going to be a bit messy like this. I'll call it A there. No. I there. There we go. Okay. A. I. All right. No. All right. So no white. That means the first one had to be red and blue, which is 15 over, what did I say? 20, 15, 6, 21. 15 over 21. And then the second one had to also be red or blue again, and it's with replacement, so you're replacing it back. 15 over 21. That's your answer for I. Double I, you had to get one white. That means you could have had the first one white, could have been white, and then red or blue, or it could have been red or blue and then white. So the first one, for it to be white, would be 6 over 21 multiplied by, and it's being replaced again, so 15 red or blues out of 21 plus, and then same answer, right? Pretty much. Red or blue is 15 over 21 times 6 over 21. That's your answer for double I. And triple I. For them to be two whites, it had to be just white, white, which means 6 over 21, then you replace it again and you get another 6 over 21. And that's your answer for that. Anyone confused about how I got any of those answers? Okay, for without replacement. All right, so I without replacement. Okay, so you're not meant to get no whites without replacement now. So the first one's going to be a red or a blue, so 15 over 21. The next one, you have one less of whatever it is, so 14 out of 20. Because you didn't replace it. Double I. It had to be white first, then you would have had still 15 of whatever's left, but you only had 20 balls to pick from. Does that make sense, you guys? So 6 white, and then the rest has to be 15, and you can see 20 take away 15, there's 5 white balls, which would make sense because you just selected one at the beginning. Plus, and then pretty much the same math. It'll be 15 over 21 times 6 over 20. So you pick any of the red or blue, and then you can't pick any of the other 14 that are left. So it's going to be 6 out of 20. And the last one is obviously 6 over 21 times 5 out of 20. All right. Brilliant. I think you guys have killed that now. There is a 51% chance of giving birth to a boy. The family has 4 children. Construct. Just show the number of boys in the family. All right, let's start 10.03. So, mean or expected value. The expected value, E of x, of a probability distribution measures the center of the distribution. It is the same as finding the mean or average, which has a symbol mu. This, we say it as mu. It is the expected value of the random variable. Okay? So E of x and mu or mean are the same thing. We use x with a hat, x bar, for the mean of a sample and mu for the mean of a population. For probability distributions, we use the population mean. The sample mean is an estimate of mu, and as the sample size increases, the sample represents the population better, and the value of this would approach this. Now, I believe, I haven't looked into this syllabus too deeply yet, but I believe this won't be in your syllabus because this should be more university-based work, but we'll see. So the sample mean should be university work. I think we're more looking into population mean. But anyway, sample mean, it's just for, it's an estimate, it's estimating your actual population mean. Okay. All right, easy. Look, how do you find average? I think you guys remember you find average by multiplying your score with your frequency and then dividing it by number of frequencies you have. You guys remember that? Or you just add up your score of 5 7 times and then divided by number of frequencies, right? So adding your frequencies gives us a total of 30. That's how you did averages usually. If you're trying to do expected value now, all you're doing is you're working out the probability of that occurring, so your relative frequency. No, sorry, what am I saying? It's the same thing, it's average. Sorry, relative frequency. Don't worry. I was going to confuse you there. Lucky I stopped. So you just find your expected value is just your average. 5 times 7, 6 times 9, 7 times 8, 8 times 3, 9 times 2, 10 times 1. Add it all up, divide it by 30, and you're done. Okay, just normal average. All right, that one there. Sum of, this should have been sigma f of x, sum of x. Okay, that's what I was trying to do. It's your E of x can be thought of as the sum of your x times the probability of that x occurring. So E of x, that you would need, I think you guys should write that. E of x, which is mu, is equal to the sum of your scores multiplied by the probability of the score. That gives you the expected value or your mean. Some of your scores multiply. Okay. Find the expected value of this discrete probability distribution. Okay, the expected value would just be this multiplied by this, plus this multiplied by this, plus this multiplied by this, plus this one. And there it is. 1 times 0.1 plus 2 times 0.3 plus 3 times 0.2 plus 4 times plus 5 times this. Any questions there? In a game of chance, Bethany tosses 2 coins. She wins $10 for 2 heads, $5 for 2 tails, and nothing for a head and a tail. Find the expected value of this game. So she wins $10 for 2 heads, $5 for 2 tails, so no heads, and nothing for a head and a tail. So nothing for a head and tail. Okay. $10, $5, cool. So we can make x equal to 0, 1, and 2, where x equals 0, 1, and 2 is the number of heads, which is what I was saying, right? So when you're seeing 2 tails, you think of it as 0 heads, 2 heads, and then 1 head. 1 head means the other one has to be a tail, of course. So no heads becomes a quarter of the time, right? Because of head, head. Sorry, tail, tail, which is half times a half, it's a quarter. 1 head is head, tail, or tail heads, so that's half of the time. And then 2 heads would be also a quarter again. Now we also know the probability of these each occurring. So, sorry, the amount that you win. So if you got, what was it? You got 2 tails, it was $5. So 2 tails, which means no heads, you got $5. So at $0, sorry, at $5, all right, at $5, you got it was a quarter. I'm just going to put it underneath, it's easier for me. So 0 heads, $5. 1 head, you win nothing. So for 1 head, you win nothing. At 2 heads, you win $10. So 2 heads, you win $10. So in other words, $10 you win a quarter of the time, $5 you win a quarter of the time, and then $0 you win half of the time. And the expected value of that would be 0 times half plus 5 times a quarter plus 10 times a quarter. So a bit more work required for this one. You've got to first work out your probabilities, then you've got to work out your expected values of each value of the amount that you'll be making. Okay. And then what is B? If the game costs $5 to play, would Bethany expect to win or lose money in the long term? Well, if you expect to make $3.75 and it costs you $5, you expect to lose $1.25. So since the game costs $5, but you expect to win $3.75, you would expect to lose money in the long term. The casino, for example, and any of the gambling games, all have negative expected value. So they've all been calculated to make sure that you will always be losing money. That's just how these the games work. So very bad. So even if you think you've won, even if it was like you won $5, let's say, in a game, the expected value is always calculated to become negative. Give me a second. All right. You can find the expected value in your calculator using the statistics mode in the same way you could find mean of data in the previous. Yep. Find the expected value of this discrete probability distribution. Easy. It's just 0 times this plus 2 times this plus 4 times this plus 6 times this plus 8 times this. Yeah. No, I'd rather you guys just do it mathematically. I mean, I could show it to you. It's pretty straightforward using the calculator, but I don't want to. I feel like it's better for you guys to just know it that way, especially doing the extension questions. You can solve problems using expected values. Thank you for telling us that. It says for the probability, I like to do B. It says for the probability function below, evaluate A and B given that the expected value is 2? Well, what do we know? We know that, okay, what do we actually know? We've got to find A and B. Can anyone give me any I don't know, tips on what I've got to do, or anything that comes to mind?
Well, if it's got equal 1,
Yeah,
I was
okay.
A plus B plus 0.2 plus 0.1 equals 1,
Yeah,
and solve it
beautiful.
like an.
Yes, absolutely. So A plus B becomes 0.3. 1 take away that becomes 0.7. And what else do you know?
E of x equals 2.
So then do you know how to do E of x now? This times this plus this times this plus, yeah?
Yeah.
So 1 times A is A plus 2B plus 0.6 plus 0.4 is equal to 2. And then, like always, when you're missing 2 letters, you've got to solve simultaneously. So you know what's going to happen. A plus 2B equals, I think that becomes 1. 2 take away 1 is 1. Subtract everything. That gets me negative B, negative 0.3. B equals 0.3, which means A equals 0.4. Probability of selling a red car based on previous experience is 35%. Find the expected number of red cars sold in 1 week if a dealer sells 2 cars. So both cars are red, 1 red, or no reds, right? One more time. 2 cars. So 2 reds, or 1 red, or no red. And you know the probability of a red car is 35%. So let's see. Probability of a red car is 35%. So probability of not a red car is 65%. So, like I said, 0 reds would be 65 and 65. Again, Andy, just to make it clear, it's not about like you're picking one so you're losing. It's the percentage, like the probability of you picking a red car is, it's just on average is 35%. So not getting a red car is 65, and then again 65. Sorry guys. And then again, probability of selecting one red car would be not having a red car and then having a red car, or not having, having a red car and then not having a red car, whatever. It becomes that. Then we get it. And then pretty much to do the expected value, we're going to multiply zero red cars with the probability of getting 0 red cars, 1 red car with the probability of getting 1 red car, 2 red cars with the probability of getting 2 red cars, which is 0.7. So it is expected that when 2 cars are sold, 0.7 of them will be red. How cool is that? That's what you're doing. So it is expected that when 2 cars are sold, 0.7 of them will be red. This is really high level mathematics, right? Just so you guys understand this, because this was not in the syllabus before. It was part of statistics in university, first semester, and really important skill to understand. All right. Round to the nearest whole number, we could expect around 1 car to be red. This answer would be more meaningful for a larger number of sales. Yeah, of course. Okay. What was B? Oh, we just did B together. There it is. All right. Those are okay. Maybe we'll start off with an easier one first. Okay, that was pretty much going to be the exact same as before. Please do question 4. Start right doing question 4. Okay. I'll start it as well now. P plus Q must equal to 0.4. And we know that 3P plus 7.25, which is 1.75 plus 8 times 1.25. 2.8 plus 9Q is equal to 6.35. And I would times this one by 3. Subtract, that becomes 6, that becomes 0.6. Q equals 0.6 divided by 6, obviously 0.1. And then P becomes 0.3. Okay. Anybody have any questions on that one? No? Okay. Let's try. I guess we'll try it. Let's try number 9. Let's see if we can get this out together. In a game, 2 dice are rolled and the difference between the two numbers is calculated. The difference between the two numbers. Okay. Do we all understand what I've just done there? I just worked out the difference of all the different, I guess, scores that could occur. In a game, 2 dice are rolled and the difference between the two numbers is calculated. And just so you guys know, I'm not doing this because I'm teaching it to you. I would actually do this in my exam. So this is, however I teach it to you, is what I would do, what I would expect you guys to be doing in your working out as well. A player wins $1 if the difference is 3. Okay, so maybe the same as before. $1, the difference is 3. So that occurs 1, 2, 3, 4, 5, 6. So $1, 6 out of 36 times. $2 if it is 4. So 2, 3, 4. 4 out of 36. $3 if it is a 5. $3 if it is a 5, so 2 out of 36. And obviously you would expect $0. So I think it's safe to say $0. I'll just put it down here. For the others, right? So for anything else, which is 12. So 24 out of 36, you would win $0. Any questions there? Draw a probability distribution table for the winning values. So for the winnings. $0, $1, $2, or $3. Okay. So, A. P of X. 0, 1, 2, 3. 0 occurs 24 out of 36 times. 1 would occur, or $1, you would get $1 6 out of 36 times. $2 you would get 4 out of 36 times. $3 you would earn 2 out of 36 times. Cool. Find the expected value. That's easy now, isn't it? The expected value is you would get 0 times 24 out of 36 times plus 1 times 6 out of 36 plus 2 times 4 out of 36 plus 3 times 2 out of 36. Plug that into your calculator. Should give you 8 on 36 plus 6 on 36, which is also 1 on 6, 5 on 9. So 0.55 or 56 if you want to round. So if you play this game, the idea is you expect eventually to win 56 cents. Okay, now the first game you could have won, you could have been super lucky, obviously. You could have won $3. That's great, and you should have walked out. The idea is, but if you keep playing this, you are expected to win 56 cents eventually. Now, even if you actually win $3, the logic behind it is you haven't actually won $3, you have actually only won 56 cents. Because eventually, as you keep playing it, you'll lose money because it'll probably cost you some money to play. You'll lose money, and eventually, as it all adds up, you're going to get to 56 cents. Okay, that's the logic of expected values. But anyway, C, it costs $1 for a player to roll the dice. How much would the player be expected to win or lose? It's very easy. You're going to lose. So you're going to lose 0.56 minus $1 that it costs you to play. You're going to lose 44 cents every time you play. Now, you paid $1, right? I just want to make sure you guys understand this. So if you paid $1 and you eventually won $3, now obviously that means you really won $2 because $1 was yours, and if you never played, you would have kept your $1. So the fact that you really won $2 is the interesting bit that a lot of people don't understand. And then if you keep playing, you will eventually be at a loss of 44% or 44 cents if it's only $1. So you're losing pretty much all the time. And that's what I was trying to say, like all those gambling machines, all those casinos, everything like that, they're not only you're not losing here, the expected value is negative. So this is already at a negative, which means it'll be like this, negative 0.56. Then you've got to spend $1 to actually play. You're always going to be losing. Anyways. All right, any questions for that one? You guys are killing it, you're doing well. What's the variance? Okay, variance and standard deviation measure the spread of data in a distribution by finding the difference of each value from the mean. So it's how far it's spread away from the average, right, from the mean. Variance is the square of standard deviation. So variance variance, which is this sigma squared. That's variance. Cool. Sigma, just sigma, is the standard deviation of x, which is the square root of variance. So standard deviation is the square root of variance. Okay, and we continue. So once you know that, you know variance is that. Okay, I'm just going to write a few of these. Variance of x is the sum of your score minus your average squared multiplied by the probability of each one occurring. Okay, one more time. Variance is the sum of your score minus the average squared times the probability of it occurring, of that score occurring. So I'm sure we'll see a question soon. And that is also the same as saying it's the